Hello everyone, welcome to the P1 program. This lecture is called P108.5. Okay, so in this lecture I'm going to give you an idea about the drag force, right? So drag force and viscous force. So what is drag and viscous force? The most of the universities, they handle these things very subtle, right? So they don't explain too much detail and they don't evaluate much detail, but we are going to look at the actual physical effects of drag force and frictional force, air drag or viscous force. So let's get to understand what is a drag force. So if you're throwing a ball, if you're a person, you see, like this, right? So if you're a person like this and you are going to throw a ball in your hand, and you're going to throw it like this, right? If it was absolute what vacuum, there was no air, then there is no friction from the air, right? So basically what that indicates is that the angle of your throw will be the same as the angle of this angle. So we have did this similar problems in projectile motion in the earlier part of the lecture. So this angle will be the same. So if there is a friction or air drag, that means that this ball is not going to reach the same point, right? So it's going to be in a different point because the air drag will make it go slower and slower, and it is going to fall down to a different point which is shorter than the actual range of a projectile, right? So this effect is called air drag or drag force, which is acting on that ball. So the basic experimental ideology behind force is that this force, which is F drag, which is equal to, or which is proportional to, the square of the velocity of the ball, and it is proportional to the density of the air, right? So it is also proportional to the surface area or cross sectional area of the ball. Okay, so the cross sectional area of the ball. So we have to now introduce a proportionality constant, and we can call this as fd. F drag must be equal to some c. Here based upon historical data, we are using a constant which is called cd by 2. This is a constant. Cd is a constant. Now it says coefficient of air drag, right? So cd by 2, v square density rho times a. Okay, so cd has a peculiar value here. So cd, let's call this equation 1. So this is equation 1, right? So this is equation 1, and cd has a special quality here. So cd for air, right? So cd for a sphere, it's based upon the shape of the object. Cd will always depend on the shape of the object. So cd for a sphere is around 0.47 in the air, in the atmosphere. So for a cube, it is based upon, it doesn't matter where it is, if it is in a fluid or in a liquid or in honey or anywhere, the cd will depend upon the shape of the object. Okay, remember that. So cd for sphere is 0.47. For something called a cube, right? A cube cd is around 1.05, so it's much higher for a cube, right? So a cube will fall much shorter, right? Much shorter than what a sphere. Okay, so that's the basic understanding of the idea of cd. So coefficient of drag, so cd for a cylinder is around 0.82. Okay, so for cylinder, so all that in place. Okay, understanding of the coefficient of drag. Now viscosity is somewhat different, right? Viscosity comes in when you have a smaller velocity. Okay, effectively smaller velocity. You have a piece of glass, a glass container, and there is honey in it, right? So there is honey inside this glass container. Okay, so if you drop a metal ball down onto this thing, right, this ball is going to go through this honey with some velocity, and this velocity will be much shorter, much smaller than a velocity of a ball which is free falling in air, right? So the frictional force or drag force inside this container of liquid is much higher than that of air. So there is some factor. This force is actually called viscous force. It is different because viscous force is different because it the dependence of air drag, right? The basic dependence of air drag is very much different, right? So why is it different is because air drag or force of drag is usually uh, a combination of F air drag component plus F viscosity component, right? So it is a combination of drag force and viscous force. So what's the difference is that this component accommodates the pressure component, right? So this component, the frictional component, okay, this component accommodates for the friction, and this component is there for the pressure of the liquid. So when the object is going to start moving faster and faster, this component is going to disappear and this component is going to take over. Okay, so the drag component takes over. Okay, so remember that. So what is the viscous component? Okay, there is some law called the Stokes law. Okay, so there is a definite law called the Stokes law. Stokes law states that, so Stokes law, so Stokes law states that F viscous, right, viscous force must be proportional to what? The velocity. The velocity, and it must be proportional to the radius of the falling object, right? So this is, earlier it was proportional to v square, now it's proportional to v. Okay, so you can see the difference. And earlier there was density and air, right? So air drag was actually a pressure component. Sorry, this I made a mistake here. So this is actually the pressure component. Okay, so this is not the case. This is the pressure component and this is the frictional component. Okay, okay, that's a mistake, a human mistake I made. I'm sorry about that. Anyways, the here we have the density component. That means it's closely related with the pressure, right? So density and area is there. Here we have the radius. So it's actually the area, surface area and all that. So how much friction it has, right? Viscosity is the friction that is appearing on a body that is moving under the influence of any force inside a liquid. Okay, so this force, so we have to introduce a constant here, right? So Fv must be equal to, for historical purposes, right, historically and based on measurement, we have something called the 6 pi eta. Okay, 6 pi eta, which is the constant here. Okay, so forgive me for that, there is no way around it. So eta is the value which is under. So why is it looks like 6 pi eta? Because we have measured eta for in earlier times, eta was measured and eta was data based, right? So the data of different materials, the different values of eta is actually measured, so that's why the 6 pi eta comes in. Okay, so making sense for that constant. So that's the viscous force, right? So let's write down what the two equations are. So F must be equal to, total force, drag force must be equal to F drag plus F viscous. So F drag is actually equal to what? CD by 2, okay, V square density times A, right? Density times A. And the viscous force, which is equal to 6 pi eta, which is a constant here, and is proportional to V and R. Okay, so that's the equation which you must remember. Okay, so let's call this equation 1, and it has two equations. Let's call it equation 1 and 2. Okay, so two equations, F viscous and F drag. So we have actually explained the foundation here. Now what I'm going to do is that I'm going to understand what happens when you actually throw something inside a liquid. Okay, so that's what I'm going to understand. Now this has a v square term and this has a v term, remember that. Okay, now let's look at a body, an actual body falling, right? Falling into a liquid. So there is an actual body falling inside a beaker, and it is going to fall down, right? Fall down, and it is going to dip into the beaker, right? Of water or any viscous fluid inside. So what happens to its velocity, right? I need to understand what happens to its velocity. So I have these theorems here, two theorems, two theorems, not theorems, but two equations here. So how does it help me, how does it help me to find out the velocity, right? Velocity of this particle at real time, right? How can I find it out? Let's find it out. So let's write down the equation of force here. So F drag, if it is for, okay, let's assume that it is moving at a higher velocity, so there is no, the viscous term vanishes, so Fv vanishes, Fv is equal to 0. Okay, let's assume that. Now there is only the what, drag force here. Okay, so if that's the case, then we can say Fd must be equal to Cd by 2 times V square rho A, right? It's the same equation. Now I can, using equivalence principle, I can say F force must be equal to Ma must be equal to Cd by 2 V square rho A. Now what I can do is that I can write it down like that: m times dv by dt, right? A is dv by dt times Cd by 2 V square rho A. Okay, so now what I can do is that I can separate the variables here, and I can separate the variables, and let's simplify this. Okay, let's do some simplification. I don't need to always write all this this whole thing. Okay, so I'm going to call down Cd by 2 rho A. These are the constants here, right? So V is not a constant, the V square is not a constant, the all other things are constant. So I'm going to call this as what, I'm going to call this as a big constant C. Okay, some big constant C. So I'm going to simplify this equation. So m dv by dt, so maybe let's call this whole thing a constant. Okay, m times dv by dt, let's call that thing as well. Okay, so let's mass is also a constant, so m divided by m as well. Okay, so it's much more easier now. Okay, so dv by dt, so dv by dt is, has now become some c, a big constant, times v square. Okay, so we have simplified that. Let's find out what the velocity. So velocity for something falling, falling with some initial velocity v0, right? The initial velocity was v0. As it enters into this beaker, the velocity is going to decrease, or whatever. So if it is going to decrease, the velocity will become the final velocity v, right? At time t0, t is equal to 0 to some time t. So let's do separate these variables. So dv by v square must be equal to c times dt, right? So now what I can do is that I can integrate both sides under the limit v is from v0 to v final velocity, and c is from t is from 0 to t, right? I can integrate that. Okay, these are simple steps. Now if I do that, what I'll get is 1 by v square is minus 1 by v, right? So it's minus 1 by v, integral of that in the limits v0 to v must be equal to, okay, must be equal to what, minus uh, minus some c times, is equal to some what, c times t, right? So c times t minus c times t from 0 to t. So what you get is what, 1 by is equal to minus 1 by v minus 1 by v0, right? So when you substitute those values here, must be equal to some ct. So you get, if you simplify, you can take the v0 to the other side, and you get v, okay, you can take the reciprocal, and you get v must be equal to some v0 by 1 plus some v0 what, ct, right? So you get that. Okay, so let's call this is the velocity here. Okay, this is the velocity actually found out. Now you can see the v0 is a constant, and v0c is a constant. Okay, v0 is a constant and v0c is a constant, right? So this has a form of some equation 1 by 1 plus, okay, 1 plus what, t, right? It has an equation 1 by 1 plus t, the form 1 by 1 plus t. So how does it look like? So v is equal to 1 by 1 plus t. 1 by 1 plus t looks like something like, let's plot that. Okay, so it looks like what, this, okay, this, okay. So that's how it looks like. Okay, 1 by 1 plus t, v and t, v is equal to 1 by 1 plus t. So that's how it looks like. That means it's going to decrease, right? It's going to decrease as t gets bigger and bigger. It's going to decrease, and it's going to reach, and it will be an asymptote, right? So it will actually gradually become a stable value, smaller and smaller, whatever that fixed value is. Okay, let's call that some basic value. So it's going to gradually decrease. That's what going to happen. So understanding the result, you can see that this, when you drop something here, even if it is faster, right, very fast, so the v square term is actually there, actually interacting with the whole thing. So it enters into this fluid, and it's going to go start become slower and slower and slower, and then finally stops. Okay, so at an infinite time, right, at an infinite time it is going to finally stop. So that's what's going to happen. So it's actually very much okay with our logic, right? So it has no violation with our logic, so it's theoretically correct. Okay, now what I'm going to do is that I'm going to evaluate what the velocity is for the viscous force. Okay, let's do the viscous force. So so if you, okay, let's have a material, a jar, and which is filled with honey. Okay, a jar filled with honey, and I'm going to drop a small ball. Okay, small ball into this. Okay, okay, so have some radius here, okay, with some velocity v. Okay, so I'm going to drop it like that. So I can write down the viscous force, the fv must be equal to 6 pi eta, right, times vr. These are constants here. 6 pi eta is a constant. Viscous velocity is here, and the radius of that ball is here. Okay, so that's the situation. So if I do that, then I can write down that the, here the ball is under the experience of gravitational force, right, and the viscous force is acting the opposite direction. Fv is acting the opposite direction. So you can write down that the total force here, which is F gravitation minus F viscous, must be equal to, using the equivalence principle, some ma, right? So that's basic. So now we can say gravitational force is mg must be equal to, or sorry, minus 6 pi eta vr must be equal to some m times dv by dt, right? So I just substituted those gravitational force. The mass m is the mass of the ball. Now I can do, what I can do is that I can rearrange this thing. Okay, maybe before that I'm going to call 6 pi. Okay, let's divide this whole thing by m. So you get g must be equal to some 6 pi, sorry, g minus, I'm sorry about that, eta v by m, sorry, eta r by m v. Okay, v is a variable here, so m times dv by dt, and I'm going to call this thing g minus 6 pi eta r by m, right? I divided m also here, so this also cancels. So 6 pi eta r by m is, can be called as some constant c. I want to avoid that constant right now for the calculation. So this must be equal to dv by dt. I just did a simple thing, right? So it's easily imaginable. Now what I'm going to do is that, so now what I'm going to do is that I'm going to rearrange this just as we did last time. Rearrange this thing and find out, separate these variables. So you get dv, right? So you get dv by g minus cv must be equal to dt, right? Okay, so you get that, And now what you can do is that you can integrate with the limit, integrate over the limit. So integral what, v is equal to 0 to some v of t, right? And on this left side you can integrate 0, t is equal to 0 to some t, final t. Okay, you can do that. Now that result will be, what will be that? So it will be on this side. I'm going to do something fishy here. Okay, so you have to be careful here. I'm going to do something because I want the result in some good form, some beautiful form. So that's why I'm going to do something very creepy here. Okay, I'm sorry about this. So what I'm going to do is that I'm going to divide the denominator. Okay, divide the denominator with what, c, and then multiply with the minus sign. That's all I'm going to do. So I'm going to divide the denominator with c. So I get integral, I'm going to write it down as easy as possible. So v of t times dv by, I'm going to divide it by what, divided by c. So and I multiply it with the minus sign. Okay, so you get what, v minus g by c. Okay, okay, I did that. Okay, and on the right side what you get is the, when you when you divide it with c, now on the right side you get what, minus integral t0 to t dt with a c, right? I just multiplied with the c, which I have taken as in the denominator, which I have taken in the denominator, I multiplied in the right side. So now I got dt. Okay, so that's what I'm going to do. Now what I'm going to do is that with a minus sign, I also multiplied with a minus sign. So I hope it is clear. I think I made it clear. Okay, I did it right. Now what I'm going to do is that, so I'm going to solve this equation right now. So I just wanted it to be in a nice form, that's why. So 1 by v minus gc is of the form 1 by x. So 1 by x is log x. So you get log of v minus g by c, right, within the limit 0 to v must be equal to minus c t within the limit 0 to t. Okay, so it's very simple. It's very simple as it is right now. Now what I'm going to do is that I'm going to substitute those values, evaluate those values. So you get log v minus g by c will look like what, log v minus g by c. When you substitute v here, right, for v you get log v minus g by c. When you substitute 0 here, right, you get minus log minus g by c, right? So minus, okay, sorry about that. So minus g by c, right? Okay, I just substitute those values of definite integrals, and on the right side you get minus ct, right? Okay, it's very simple now. So this can be written as log v minus g by c by minus g by c. Okay, you can write it down like that. So that will be equal to minus ct. Okay, it's very simple. Log a minus log b is log a by b. That's the principle I used. Now what I can do is that I can exponentiate the both sides, right? So I can take the exponential of both sides. So I get what, so you get the log will disappear and you get, okay, v minus g by c by minus g by c must be equal to minus ct, right? So that's what you get when you when you take out the when you take the exponential. Okay, sorry, e raised to minus ct. Okay, what am I thinking? Okay, sorry. So e raised to minus ct. Okay, so that's what you get. Okay, now this has become much more simpler now. So you can write down that v minus what, g by c minus g by c is equal to minus g by c e raised to minus ct, right? So it has become much more simpler now. And what you can do now is that we can take the minus g by c out the right side. So you get v is equal to, and also the if you look into this you can see it is what, g by c can be taken outside and you get 1 minus e raised to minus ct, right? Okay, and you take it to the right side. Now what I'm going to do is that, let's call this equation what, 4, or I guess 4, I guess. Okay, so let's call this equation 4. Now what I can do is that I can substitute the values of C. Okay, what was C? So C was this complicated thing. So I called C what was C? C was 6 pi n eta r by m. Okay, that was C. So I'm going to substitute that value of C in here, and you get V must be equal to 6 pi eta r by m, right? So it's a gm by 6 pi eta r times 1 minus e raised to minus the same thing, 6 pi eta r by m times t. So that will be the velocity. So the velocity of the ball inside the liquid, viscous, under the influence of viscous force, when it is moving in a smaller velocity under the viscous force in the frictional part. So that this is the equation for the velocity. Let's call this equation 4. Okay, this is equation 4. These two are the same equation, so it's, let's call it the 4.1 and 4.2. Okay, for reference if you want, 4.1 and 4.2. So that's the velocity. Now let's plot it, right? Let's see what it looks like. So this equation, if you look closely, okay, this whole thing, whole mess, let's clear those mess. If you look at this, so it looks like some V must be equal to some constant times 1 minus e raised to some constant times t, or you can say it is of the form what V must be equal to some 1 minus e raised to what, e raised to t, right? E raised to minus t, right? It was minus sign. Okay, minus t. Okay, that's very important. So some minus t. So this is the form of this equation, right? So this is an exponential function which is decreasing exponential function, but it is increasing because there is a 1 minus of e raised to minus t, right? So this was e raised to minus, e raised to x is increasing, e raised to minus x is decreasing, 1 minus e raised to minus x must be increasing. So let's plot it. Let's plot, and how, let's see how beautiful it looks like. So if you plot it over v and t, right? V and t, v must be equal to some 1 minus e raised to minus t. Looks like it goes up to some infinite, some value, right? Some fixed value, and then it asymptotically reaches that value, right? So this is slowly going to, this velocity is called terminal velocity, vt, right? So what is going to happen is that, okay, this is the plot here. So what is going to happen is that when you insert this thing into a beaker, so this thing is actually going to start off with a higher, smaller velocity. So when you first pull this ball, okay, understanding this part is much more critical. So just keep your focus, right? So if you put it in a piece, in a jar of honey, then first of all it's going to stop. Okay, first of all it's going to stop because it is 0 here. Okay, so it's going to stop immediately, and then starts to merge into this liquid, and then increase its velocity slowly, and then get to a velocity v of t, which is terminal velocity. So maximum velocity, right? So this is the maximum velocity here, this part, and then it's going to remain in the same velocity and moves down to the ground. Okay, this is something that is absolutely unintuitive and non-predictable. You cannot imagine this happening, right? So if you look at this actually happening, if you try this out, you will see the exact same thing happening. So we have mathematically found out what's happening. Okay, that's a very big thing if you don't realize it. So that's v terminal here. Now, so let's write down the equation of v terminal. Okay, and let's find out something much more interesting. So v must be equal to some mg by 6 pi eta r times 1 minus e raised to minus 6 pi eta r by m, right? That was the constant, times t. Okay, that's the equation. So what happens the after so how can you find out the terminal velocity? That's the important factor here. So we know that it reaches some maximum value, right? So the terminal velocity will be reached. So what happens, what is the terminal velocity? How can you find out that? So if you look closely, you see that this plot is going up and up and up and up, right? So as time goes on, right, time goes on and on, you will see that the velocity will be reaching this value, right? So the velocity will actually be reaching this value and asymptotically reaching to this value as time goes up on and on. So time as goes to infinity, so it must be at velocity vt, right? So that in principle. So what we need to do is here is that we can put time as infinity. So let's put out time as infinity. So if you put t is equal to infinity, you get v of velocity, terminal velocity vt. So that must be equal to some mg by 6 pi eta r times 1 minus e raised to minus infinity. So what is e raised to minus infinity? E raised to minus infinity is just 0. So e raised to minus infinity, everything else vanishes. Okay, so that is just 0. So you get vt, terminal velocity, is equal to some mg by 6 pi eta r, right? So that's terminal velocity. Very easy, right? Very easy, very elegant, and very useful, right? So now you, if you don't know the mass of the object that you are putting inside the beaker, right, on the viscous fluid, so what will you do? What, how do you know the if you know the density? Let's rewrite this in terms of density. So mass will be some density times volume, right? So mass by volume is density, so mass is some density times volume. So mass, if it is a spherical ball, if you are putting a spherical ball, then mass must be equal to some what, density times volume is 4 by 3, what, 4 by 3 pi r cube, right? So 4 by 3 pi r cube, right? R cube. Okay, so let's substitute that back into this equation. M is equal to rho times 4 by 3 pi r cube. So v of t will become some uh, m will be some rho times 4 by 3 pi r cube times g, right, by 6 pi eta times r, right? So this thing cancels and you get what, 2 by 9, right? 2 by 9 rho r square g by, yeah, rho r square g, pi and pi also cancels, so rho r square g by eta, right, eta. Okay, so that's the terminal velocity of anything. So you can find out the terminal velocity with this equation. So this is very important equation. This is vt, general equation for vt, right, terminal velocity. Now what you can do is that we can also find out the distance travel. So the distance travel will be some integral of 0 to t v dt, right? So we have done this so many times. So integral of velocity, the area under the curve of velocity graph, is the distance or displacement travel, right? So the displacement, they're both the same since it's going down straightwards, right? So displacement is like that. So what we can substitute the values, let's for air drag, right? Let for air drag, right? So v for air drag was what, for air drag was v was equal to some, if you look back at the equation, what, one equation 1 or something like that. So let's look back, we have done a long way, we have gone a long way. Anyways, let's look back and see what the equation of air drag was, right? This was not it. Okay, air drag was what, the equation was like, okay, v is equal to some g by c, right? G by c times equation 4, g by c times 1 minus e raised to minus ct, right? So that was the equation. So let's use that equation and find out how much distance it goes, right? So how much distance it goes, so it will be it will be integral, okay, integral 0 to t v times dt, which is g by c times 1 minus e raised to minus ct dt, right? So now you can write down the constants if you want, but before that let's do something. So let's integrate and you will get g by c times t under the limit 0 to t, and then on the other thing is minus g by c times e raised to minus ct by minus c, right? Minus c, right? So that's what you are going to get under the limit 0 to t. Okay, I just integrated it. So you get g by c t minus 0 minus g by c, you get g by c square, right? G by c square e raised to minus c t, right? E raised to 0 is just 1, so you get minus another minus and minus plus, right? So there is a minus as well, so you get minus g by c square. Okay, so that's what you get. You can do this, it's very simple. So g by c t, I'm going to write down, take the c square outside, and you get e raised to minus ct minus 1. So that's the distance travel. Okay, that's the distance travel. So everything can be found out, right? It's not complicated, it's everything can be found out if you follow the physics. Okay, what we have done is just write down the equation and solve it. Okay, this is a very good example of how to solve problems as well. So I hope you guys enjoyed this. This is very good. We have found out the terminal velocity, we have found out the what the distance traveled by this, we have found out how much velocity it will have in both cases, and we have found out a lot. Okay, so I hope you guys enjoyed it, and all the very best for you guys. Okay, thank you for watching. Please subscribe.